Hey everyone, and welcome back to Edit. In this lecture, we are going to study how we can convert an octal and an hexadecimal number to a binary number. Okay, so before wasting our time, let's start. So before jumping into the conversion from octal to binary or hexadecimal to binary, I would like you to focus on the thing which we studied in the last lecture, the sequence of binary number. Specifically at this point, the 3-bit binary number conversion to 3-bit binary number equivalent into the decimal. If you see this, the 000 was equivalent to 1, 001 was equivalent to 2, 100 was equivalent to 4, and 111 was equivalent to 7. Here the total possible combinations were 2 is to power 3, which were equal to 8. Now we know that this binary number system is positional number system, which means that each bit has its position weightage, right? So will I be right if I say the position of this is 1 and the position of bit 1 is 2 and position of bit 2 is 4? So the total weightage of the position can go up to 7. So this is the max weightage which can go, right? Now let's go back to our understanding of octal number. We know that for octal number, this radix r is equal to 8, which means the combinations of symbols which are possible are 0, 1, 2, 3, 4, 5, 6, 7, right? Don't you think all these combinations are present here? And don't you think the binary equivalent of these numbers is this? Making sense? No? Then just bear with me for an example. So let's suppose you are given an octal number, something like 712.456 base 8, which means it's an octal number and you're asked to convert it into binary number. What you have to do is you have to simply write the binary equivalent of each digit of this octal number. So simply go to this table and look at the equivalent binary number of this equivalent octal number. Now see, this decimal number is going till 8 only, so I can say that this is also representing the octal number, right? So if I go back again over here, and if I want to convert this octal number into the equivalent binary number, what I need to do is each digit I have to write its binary equivalent from this table. So this 7, it has binary equivalent of 111. I'll write down 111. And then this 1, it has binary equivalent of 001. So I will simply write 001. And then this 2 has equivalent of 010. I will simply write 010. And then this point as it is. And then this 4, it has equivalent of 100. So I will write 100. And then this 5, it has equivalent of 101. So I will simply write 101. And then the 6 has equivalent of 110. So I'll simply write 110. This converts your octal number into the equivalent binary number. Easy, right? Now let's try. Let's do this problem as a homework statement for you. 646.353 base 8. You have to convert this into the equivalent binary form. Let's try to solve one more example by ourselves. I'll say 678.123 base 8. What should be its binary equivalent? I would like you to pause the video and try to solve this question. So first of all, before approaching the solution of the problem statement, it is important to understand whether the problem statement is correct or not. The problem statement says that this number is an octal number, but don't you think it has an illegal symbol? So isn't 8 an illegal symbol? Because the possible combinations I can have is up to 0 to 7. So this 8 is not a legal symbol, right? So 8 is illegal symbol in octal number system. So this case is not, itself is not valid. Now, I hope the idea is clear to you of how can we convert the octal number into the binary number using this table where we have this positional number system. Each bit has its position weightage and we have the decimal equivalent of each. And as they were only 3 bits, the only 8 decimal combinations were there which collided with the octal combinations as well. So this was also equivalent to octal form, octal form, octal form, and so on. So we tried to understand that through an example of how can we convert the octal to binary. The binary to octal is exactly opposite, but that is something which we will see in the next lecture. Now let's try to understand the conversion from hexadecimal to binary. Okay. Now, again, before going into that, I would like you to focus over here. So this is a table. Again, we know this is positional number system, which means each bit has its own weightage. Now that weightage is 2 to the power 0, 1, 2, and 3, which means 8421. This is why we also call it as 8421 code. So that is something you can write down. 8421 code is something which we call it. Now you see this decimal equivalent and it is going till 15. Do you recall what was the value of A? In case of hexadecimal number, it was 10 in decimal, right? What was the value of B in hexadecimal number? It was 11 in decimal. What was the value of C in hexadecimal? It was equivalent to 12 in decimal. What was the value of D? It was equivalent to decimal 13, and E was equivalent to decimal 14, and F was equivalent to decimal 15. Okay. Now again come back here. Can I say it like this? 10 is equivalent to A, and 11 is equivalent to B, and 12 is equivalent to C, and 13 is equivalent to D, and 14 is equivalent to E, and 15 is equivalent to F. Yes, I can say that, right? So don't you think I have the equivalent hexadecimal format of these binary bits, or vice versa? I have the equivalent binary format of these hexadecimal bits. If you understand this concept, we are done with converting hexadecimal to binary. How? Let's try to see that through an example. But before jumping in, let's just quickly revise our concepts of hexadecimal number, which is the radix r is equal to 16, which means the combinations I have is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Now let's see an example, a random example. I'll take any number which I'll say 7, 8, A point B, E 2, which is in hexadecimal format, and I've been asked to convert into the equivalent binary format. Now, how to approach the problem? Exactly same way, but here instead of using 3 bits, you have to use 4 bits. So use 4 bits. Why I need 4 bits? Because I need at least 4-bit binary to represent a single hexadecimal digit. How? Just see over here. In order to distinguish properly, I need at least 4 bits, right? Because this MSB can go high in case of hexadecimal number system. But was this the case same for octal? No, right? Because in octal, it is the number is going till 7 and all bit toggle to this point only. So I only needed 3 bits in binary to represent equivalent octal number. So that is also something which we can write as a note. Similarly, like this, use 4 bits, need at least 4-bit binary to represent a single hexadecimal digit. So here also we need 3 binary bits to represent a single octal digit. Okay. Now let's come back to our problem statement. I need to convert this number into a binary equivalent. How I can do that? Simply go to the table, see the equivalent binary number and write it down. So for 7, it is 0111. So I will write down 0111. I'm done with 7. 8, it is 1000. So I'll write down 10008. I'm done with A is 10 equivalent 10, which means 1010. I will write down 1010 and I'm done with A. Now there's a point, so point I'll put as it is. B is 1011. I will put 1011 and then E. I will again go back and see how does E looks like. E looks like this 1110. So I'll write down 1110 and I'm done with E. Then 2 is 0010 and I'm done with the binary equivalent of this hexadecimal number system. Now you can take any random number and try to solve it out on your own. This is how we need to follow the procedure. And this is how you can simply convert any hexadecimal or octal number into the binary number. What you need to recall, what you need to remember is this sequence table of the binary numbers, which you will gradually learn automatically when you will move forward into the course. So this is all for this lecture. I hope you enjoyed this lecture and understood these conversions. I hope to see you in the next one. Bye bye.